Right now, world leaders are locked in an intense debate over a massive nuclear deal. But the real panic isn't about politics. It's about a simple mathematical rule that completely breaks common sense. Most people think making a nuclear power plant is 90% of the work and turning it into a weapon is the final 10%. But the laws of physics are completely backward. Mathematically, once a civilian nuclear plant refines its fuel to just 4%, it has already done over half the physical work required to build a weapon. In this video, we pull back the curtain on the pure engineering, physics, and centrifuges running this hidden system. Welcome to what actually is. But before we dive into the physics, we need to understand why nuclear energy is so desperately wanted in the first place. Why do world leaders care so much about uranium? The answer is staggering density. Imagine a single, tiny pellet of uranium fuel. We're talking something you could hold between two fingers. It's smaller than a marble. Now imagine a massive train car filled completely with coal. That train car is 50 feet long, 10 feet wide, and 10 feet tall. It weighs hundreds of tons. That single uranium pellet and that entire train car produce roughly the same amount of energy when burned. Now imagine switching to oil, a massive barrel of crude oil. You'd need approximately 150 barrels of oil to match the energy output of that tiny uranium pellet. 150 barrels. That's thousands of gallons of liquid stored, transported, and burned. This is why uranium is so valuable. Energy density is incredible. 1 kilogram of uranium-235 releases the same energy as 2,700 kilograms of coal. The math is overwhelming. A single nuclear power plant can power a city of millions, using fuel that arrives in small containers instead of endless train cars and truck shipments. This is why countries desperately want nuclear energy. It's clean, it produces no carbon emissions, it requires minimal fuel, and once the plant is built, it runs continuously for decades without interruption. A coal plant needs constant restocking. An oil plant needs constant delivery. A nuclear plant needs fuel delivered once every few years. But here's the catch. The same properties that make uranium perfect for generating electricity make it perfect for something else entirely. That same incredible energy density means that if you concentrate uranium properly, you can build a weapon that destroys everything in miles. This is the fundamental tension. Now let's talk about the actual uranium problem. Imagine you're baking bread at home. Your flour bag isn't pure flour. It contains two different types of flour kernels mixed together. One type is heavy, inert, useless for baking. It makes up 99.3% of the bag. The other type is light, reactive. This is your secret ingredient. It makes up just 0.7% of the bag. These two flour types are chemically identical, same color, same texture, same molecular structure, but they weigh slightly different amounts. To bake regular bread for your family, you only need 3% to 5% of your flour to be the reactive type. The heavy stuff doesn't hurt, it just sits there. But to bake an explosive wedding cake that destroys a city block, you need 90% pure reactive flour. The heavy, inert flour ruins the entire recipe. Here's the problem. These two flour types are so similar that you cannot separate them with chemistry. You cannot filter them. You cannot boil them apart or dissolve one away. The only difference between them is microscopic weight. This is exactly how uranium enrichment actually works. Uranium straight from the ground is 99.3% uranium-238, the heavy, inert type. It also contains 0.7% uranium-235, the reactive type you actually need. These isotopes are chemically identical. They have the same number of electrons. They behave identically in every chemical reaction. But uranium-235 weighs slightly less. To power a civilian nuclear plant, engineers only need to concentrate the uranium-235 to about 3% to 5%. That's enough to sustain a chain reaction inside a reactor core. Electricity flows, cities light up, hospitals run. But to build a nuclear weapon, you need uranium-235 at 90% purity. Anything below 60% is considered low enriched. Anything above 90% is weapons grade. But there's a crucial difference between these two scenarios that most people don't understand. Imagine a room completely covered in mousetraps. Every square inch of floor is packed with loaded mousetraps. Now you throw ping-pong balls into the room. At 4% purity, you're throwing ping-pong balls into a room where 96% of it is covered in mousetraps. Mousetraps everywhere. When a ping-pong ball bounces around, it constantly hits traps. It triggers them. The traps reset themselves. The chain reaction stutters and stops. This is controlled, safe, steady. The heavy uranium-238 acts as the trap. It absorbs loose neutrons. It keeps the reaction calm. But at 90% purity, you're throwing ping-pong balls into an almost empty room. Only 10% of the floor has mousetraps. Most of the room is bare. When a ping-pong ball bounces, it flies freely. It hits another ball. That ball hits another. The ping-pong balls multiply exponentially. The chain reaction happens instantaneously. There's nothing to stop it. This is unstable, violent, catastrophic. With almost no uranium-238 present, nothing can absorb the neutrons or slow the reaction down. This is the physics difference between reactor fuel and weapon fuel. It's not just about purity, it's about control. At 4%, the system is engineered to be safe. At 90%, the system becomes a runaway chain reaction. The question becomes, how do you separate two things that are chemically identical? How do you sort flour kernels by weight when they look exactly the same? The answer is centrifuges. First, engineers take solid uranium metal and convert it into a gas. Think of it like taking your flour and turning it into an impossibly fine mist that floats in the air. This gas is uranium hexafluoride. It's invisible. It flows like air. This conversion is crucial because gases are easier to spin and separate than solids. A gas centrifuge is a spinning cylinder. Imagine a playground rotor ride spinning at absolutely insane speeds. We're talking 50,000 to 100,000 rotations per minute. That's faster than a jet engine turbine. At these speeds, the outer walls of the centrifuge are moving faster than the speed of sound. This creates a material science crisis. When objects move faster than sound, any microscopic imperfection becomes catastrophic. A single grain of dust, a wobble thinner than a human hair, a micrometer of vibration. Any of these things will cause the walls to resonate. The metal will crack. The centrifuge will violently tear itself apart. The spinning tube will vaporize into shrapnel. Engineers must build these machines to impossibly precise tolerances. The walls must be perfectly balanced. The rotation must be flawlessly smooth. One flaw and the entire machine destroys itself. This is why centrifuges are so difficult to manufacture and so heavily restricted by international law. At these speeds, centrifugal force becomes powerful enough to push on individual atoms. The uranium gas gets pumped into the spinning cylinder. As the cylinder rotates, the centrifugal force pushes outward on everything inside. The heavier uranium-238 atoms get slung toward the outer walls of the cylinder. The slightly lighter uranium-235 atoms stay closer to the center. Think of it like spinning a bucket of water. The water pushes outward, but a lighter object floats toward the middle. But here's the catch. A single centrifuge only separates a microscopic amount of uranium-235. One tube, spinning at maximum speed for months, might only produce a few kilograms of slightly enriched uranium. To actually generate useful amounts of fuel, engineers must link thousands of these centrifuges together in a system called a cascade. Picture thousands of spinning tubes connected by pipes and valves in long plumbing lines. The output of one centrifuge, the gas enriched slightly higher in uranium-235, feeds directly into the input of the next centrifuge. Then the output of that one feeds into another. The uranium gas flows through the entire cascade, getting a tiny bit sweeter at each stage. Each tube nudges the concentration higher. Each connection moves the mixture closer to the target purity. One cascade might contain 5,000 individual centrifuges, all linked together. A full enrichment facility might run 50 cascades simultaneously. That's 250,000 spinning tubes running at the same time, consuming enormous amounts of electricity and generating intense heat. The pipes never stop flowing. The gas keeps moving. Each tube adds another small increment of purity. Now here's where the math gets weird. This is the counterintuitive part that makes nuclear proliferation so difficult to stop. Going from 0.7% uranium-235 to 4% enrichment is the hardest part of the entire process. Imagine you're standing in front of a massive ball pit. The ball pit contains 1 million balls. 993,000 of them are heavy metal balls. 7,000 of them are lightweight plastic balls. Your job is to separate the plastic balls from the metal balls. You can only feel the weight of each ball as you touch it. You cannot see the difference. You cannot hear the difference. You must physically touch and sort every single ball. This process takes forever. You're swimming through millions of useless heavy balls just to find the few lightweight ones you actually need. You get tired. Your hands hurt. You're moving mountains of weight just to isolate tiny amounts of the light material. This is why the first phase consumes 90% of the total energy. But then something unexpected happens. Once you've removed most of the heavy balls and your pile now contains 4% plastic and 96% metal, the remaining work becomes trivial. You're sorting through a much smaller batch. The plastic balls are now comparatively abundant. You can find them quickly. You don't need to dig through endless mountains of waste material. The remaining work is mathematically effortless. This is why going from 4% to 90% takes a fraction of the time. You need far fewer centrifuges running. You consume very little additional energy. What took months to go from 0.2% to 4% takes only weeks to go from 4% to 90%. This is why international monitors focus obsessively on the 3% to 5% threshold. Once a country crosses 4% enrichment, the hardest work is already finished. But what happens to all those millions of heavy metal balls you discarded? Where does the mountain of uranium-238 go? Depleted uranium, the leftover uranium-238, doesn't disappear. It sits in storage tanks. Massive quantities of it. Entire warehouses filled with rejected uranium. This material is extremely dense, denser than lead. This extreme density makes it incredibly useful for military applications. Tank armor plating, projectile rounds, heavy shielding. The military industry uses depleted uranium because its weight and density provide exceptional protection. The same waste product that makes enrichment difficult becomes valuable in weapons manufacturing. Here's the final unsettling reality. The physical infrastructure looks identical at every stage. The pipes are the same, the valves are the same, the centrifuges are the same. There is no separate weapons facility using different technology. There is no secret button that switches the machine from peaceful to military. The exact same engineering solves both problems. International monitors don't look for different machines. They watch time. They count spinning tubes. They check valve settings. They track how long uranium stays inside the cascade. The difference between lighting a city and destroying it comes down to mathematics and patience. The ultimate challenge of the atomic age isn't discovering a complex secret formula. It's confronting the engineering reality that the same centrifuge, the same cascade, the same physics can accomplish two completely opposite outcomes, separated only by a mathematical curve and how long you leave the mixers spinning. If you found this breakdown useful, please like this video and subscribe to the channel. Drop a comment below telling us what complex topic you'd like us to break down next. Stay tuned as we continue uncovering the mechanisms that shape the very world we live in today.